Hey, what's up, everybody? In this video, I want to take some time to talk about electrophilic aromatic substitutions. Now, aromatic compounds typically don't undergo addition reactions, but they can undergo a number of substitution reactions. Some of these include, let's say we have halogenation, sulfonation, nitration. There's the Friedel-Crafts, alkylation, and acylation, just to name a few. Now, regardless of the type of EAS you're looking at, the type of electrophilic aromatic substitution, um, a lot of these reactions actually tend to have a number of things in common. They tend to have a similar mechanism. They tend to have similar kinetic and thermodynamic characteristics. And so I want to look at all of those things in this video, the mechanisms, some kinetics and thermodynamics. But I'd like to begin our discussion by talking about the mechanism behind different types of EAS reactions. So to kick things off, why don't we talk a little bit about benzene? So I've drawn in a benzene here, and benzene is the sort of prototypical aromatic compound, right? Now, usually when you draw benzene, you don't really draw in any of the hydrogens on the benzene. You just sort of assume that those hydrogens are there. But anytime you're doing EAS type reactions, especially if you're doing a mechanism, you're drawing out the mechanism, I highly, highly recommend, strongly encourage you to draw in at least one hydrogen. And that'll be more clear, I think, later on in this video why that's the case. For now, let's just roll with it. So we have our benzene with one hydrogen drawn in. Now notice next to this benzene, we have an electrophile. An electrophile is a Lewis acid. These tend to be sort of electron deficient species, and because they tend to be electron deficient, they are typically electron pair acceptors, right? So an electrophile, also known as a Lewis acid, is an electron pair acceptor. And in fact, that's actually going to be the first step in many EAS type reactions. You're going to have a pair of pi electrons within an aromatic system reach out and grab an electrophile, right? And that's what we see here. So we have this aromatic system, then we have two pi electrons here, and they're going to reach out and form a bond with this electrophile. And notice in this process, we're going from something that is aromatic, right? This is aromatic, to something that is no longer aromatic, right? So this is not aromatic. All right, so the first step of EAS reactions, pair of pi electrons is going to flow out. You're going to get a bond formed between this carbon here and the electrophile. Now, when deciding which hydrogen to draw in, you want to draw in the hydrogen connected to the carbon that forms a bond with the electrophile. Let me repeat that because that's really important. When drawing in your hydrogens, right, you want to draw in the hydrogen connected to the carbon that forms a bond with your electrophile, all right? Really important. Now notice, once we break this aromaticity, right, we go from something that's aromatic to something that's no longer aromatic, we actually have a positive charge now in our ring system, right? And that's just because, well, this carbon down here was involved in a double bond, right? But it lost those electrons, right? These electrons went to form a bond with the electrophile, and thus we have this positive charge down here on this carbon. Now, something important to point out is that that positive charge is not actually localized at that carbon or any other carbon in particular, and this is because of something called resonance. So notice we have this positive charge on this carbon, and this positively charged carbon is located next to a double bond, right? So these electrons in this double bond, they can flow over. So now we get a double bond here, and that positive charge jumps over, right? So this can actually happen again. This positive charge is now adjacent to this double bond, right? These pair of electrons here. And so these pi electrons here can sort of flow in, and now we'll get a double bond here, And then that positive charge will be associated with this carbon now, right? So this ion that we've generated, this positively charged ion, is actually resonance stabilized. And this resonance stabilized ion that's characteristic of virtually all electrophilic aromatic substitutions, this ion is sometimes referred to as the uranium ion, right? So this is the uranium ion. This is another way to represent it. This is another resonance form of the uranium ion, all right? So anytime you're talking about electrophilic aromatic substitutions, you're probably going to form an uranium ion, all right? So that's the first step of the EAS mechanism. You're going to have something that's aromatic, and some pi electrons from that system are going to reach out and grab an electrophile, and thus you're going to generate the uranium ion. So that's the first step. In the second step, remember that hydrogen we drew in earlier? Yeah, that hydrogen is actually going to be deprotonated by some base. And that deprotonation event is actually going to restore the aromaticity of our ring system. So here we have that hydrogen that we drew in. Then we have some base over here, right? And so this base is going to come by and it's going to remove this hydrogen. And then the electrons connecting that hydrogen to the ring system, well, these electrons here are going to flow back into the ring system. And that's going to regenerate our aromatic ring. That's pretty much it for the mechanism for electrophilic aromatic substitutions. Pretty much just two steps. In the first step, you have something that's aromatic, but it's going to form a bond with an electrophile. So that's going to break your aromaticity, right? It's going to form an uranium ion, which is not aromatic. And in the second step, you're going to regenerate aromaticity through a deprotonation step. All right, so that's pretty much the basic mechanism behind electrophilic aromatic substitution. Now I guess I want to move on to sort of the thermodynamic properties associated with a number of these reactions. And we can consider thermodynamics through this energy diagram here. So on the y-axis we have energy, and on the x-axis we have the reaction progress. You could, I guess, sort of think of this as time. You know, maybe over here this is time 0, the reaction really hasn't started yet, and over here your reactants are, well, reacting with one another, and then maybe over here we've generated products. So a few things I want to point out about this energy diagram. First thing, notice that we have two transition states, and these two transition states correspond to our two steps, right? So our first step here, in this first step we generated this reaction intermediate, right, this uranium ion. And so over here, right here, this is pretty much the energy corresponding to our reactants. We're going to pass through one transition state that corresponds to step 1. And once we get over this energy barrier, we will have generated a reaction intermediate. That reaction intermediate being the uranium ion. Now we have another energy barrier here, right? And this energy barrier corresponds to step 2. So then once we get over this energy barrier for step 2, we will have regenerated aromaticity, and thus we will have our product here. So why are these energy barriers here? And really, why is this first one in particular so large? Remember, in the first step, you are breaking aromaticity. You have something that's aromatic, and it becomes something that is no longer aromatic. You know, aromatic compounds tend to be very, very stable. So because in step 1, you're breaking aromaticity, that takes a lot of energy, right? And so we're going to have a pretty large activation energy, a pretty large energy barrier associated with step number 1. Because step number 1 is such a large activation energy here, step number 1, where we break aromaticity, that's actually going to be the rate limiting step, right? It's going to be the slow step in the reaction if we're considering kinetics, all right? So that's pretty much it for the basics, at least, for electrophilic aromatic substitutions. Remember, the mechanism is essentially a two-step mechanism. In the first step, you're going to take something that's aromatic and you're going to break aromaticity, thus generating this reaction intermediate, this rhenium ion. Now, because you're breaking aromaticity, there's a pretty large activation energy barrier to overcome in order to generate your reaction intermediate. And then you're going to have to undergo a second transition state for step number 2. And in step 2, you restore aromaticity, and that's why the overall energy drops back off here in the products. So that's the basics for electrophilic aromatic substitution, but stay tuned because in other videos I'm going to talk about the specific types of electrophilic aromatic substitution, such as halogenation, nitration, sulfonation, Friedel-Crafts type reactions. So stay tuned. Thanks for watching and take care.